Welcome to Study Time, a televised home learning program produced by Rwanda Basic Education Board.
Hello students, welcome back again to this TV Learning Series program. As usual, I'm Teacher Patrick, and this time I'll be taking you through Unit 5 of Chemistry Senior 4. So in this unit, we are going to look at the periodic table. Basically, we'll look at the periodic table. And we are starting with the historical background. So I expect you to have your periodic table with you. If you don't have one, please grab a copy that is nearby you so that we can go together, because you need it, I'm very sure. So for those ones who have probably studied this unit, those who could have maybe finished this unit by the time that we went home, I expect you to follow, and then we revise together. And for those that could have not reached there, please, you need maximum attention so that you don't skip anything. Or even when you go back to school, you don't repeat that, or you go as the revision. So in the historical background, there are a number of scientists that tried to look at the arrangement of elements that were discovered by then as we look at them. And there was a lot of headache that gives this arrangement of the modern periodic table you are using there. So without probably wasting a lot of time, we are just going to go through these scientists. And if you remember, that means if you had gone through this, this is, to be sure, this is one of the important discoveries that has ever happened on Earth. The periodic table. It gives the science. If we are studying science, the origin of the science is the arrangement of this modern periodic table. If you have a look at it, very well organized and arranged. So the first scientist is by names of Antoine Lavoisier. Probably, if I pronounce the name very sure, but wrongly, please. At least you'll have to excuse me for that. So this is a French scientist, and by 1789, Lavoisier is very well known for a lot of a range of experiments, including the conservation of mass or the conservation of matter, including the theory of acids and bases, to name them. He's the first scientist to put elements together and tried to organize them. 1789, that is close to 300 years ago. So that's when he tried to organize these elements. And you know how he tried to organize them? At least what he did was the basis of the periodic table that we have today. He grouped these elements into non-metals and metals. You know, on the periodic table, if you look at the periodic table, you'll have the non-metals on the extreme right of your periodic table, and on the extreme left, you have the metals. So he's the first person at least to give that basis. But what is funny with Lavoisier, that is Don't mind about the pronunciation. So what he did, the funny part of it is that he even included light and heat as some of the elements and grouped them together with even oxygen and hydrogen. Heat and light and then oxygen and hydrogen were grouped together. Does it give sense? Anyway, according to today and the periodic table that we have, it doesn't make sense to call light an element or heat an element. So after some time, another scientist by names of Johann Wolfgang Dobereiner came up with an idea on how these elements can be arranged. And what he did, he got the elements that were known at that time. That was around 1829. So he got the elements that were known around that time and grouped them in threes. So, for example, he got elements like lithium, like sodium, and potassium. This was one group of elements that he studied, and he arranged those elements in order of increasing atomic mass. He was the first person, at least, to arrange the elements in order of increasing atomic mass. So he arranged them in that order, and then he called this a triad. He called it a triad. Tri comes from three. And then he got some other triads, as we can mention. Some of them, there are other triads, like the atomic mass of others you have, like caesium, strontium, and barium. The atomic masses, if you look at 40, this is 88, and this is 137. And something very interesting came up. When you add these atomic masses together, the average of those masses, the average of these masses, that is, if you get 40 plus 88 plus 137, and you divide by 3. Interestingly, what he got was the atomic mass of the middle element. That is approximately 88. And that was the atomic mass. If you have the periodic table, look at it, and then you see what is going to happen, what happens. You can just even add. Just look at the periodic table with the sodium, which has 23, with the potassium, which has 39, and with lithium, which has 7 as the atomic mass. When you add these 3, you will get the average of these elements will be the middle, the atomic mass of the middle element. And he tried this with other several groups, which we call triads. And he formulated a law of triads. And this law, he said that when the elements are grouped in threes, and the atomic mass, the sum of the atomic masses will be equal to the average of the middle element. And he called it the law of triads. So these are some other triads that he came up with. So the first, those that I've mentioned, the second. So we have written the second. This was the third, chlorine, bromine, and iodine. That was the third triad. When you look at the atomic masses of this is 35.5. This is 80, approximately 80. This is 127. So when you add these three, the atomic mass, the average atomic mass will be the mass of the middle element. And he came up with other triads, 3 triads. So you can ask yourself, do these triads exist on the periodic table that we have today? The answer is yes, they also still exist. But what happened? Why is it that this periodic, this arrangement was not maintained? It is because if we look at the limitations, we can also look at the limitations. The limitations of Dobereina's periodic table. Dobereina's periodic table. What could be the limitations? When other elements were discovered, they could not fit into his arrangement. Even when you look at the periodic table, if you have that periodic table with you, if you look at the periodic table, look at the elements that are together in their groups today. You will find that when you add them together, some of them would not fit this Dobereina's periodic table. So that is what happened. The discovery of some elements could not fit in, and that made it obsolete. So it was no longer in use. And again, that these triads, other elements were not even fitting in. So that is why even it is no longer even used. So we can just go through, again, another scientist by name of Newlands. This was a British chemist from England. So he arranged the elements in this form. I just want you to look at this one very closely. When you look at these elements from here you have hydrogen. If you start with the hydrogen, the lithium. When you look at this element, the arrangement, it is that if you start from hydrogen and you count 8 elements, he actually borrowed the idea of arranging elements in increasing atomic mass. And he did that by arranging his own elements. I've told you why even the Dobereina's periodic table was not used. So Newland, that is in 1864, he came with such an arrangement. Hydrogen, lithium. When you count here, from hydrogen to lithium, count 8 elements and you see 1, 2, 3, 4, 5, 6, 7, 8. Fluorine comes here. You start from, let's start from beryllium, for example. 1, 2, 3, 4, 5, 6, 7, 8. So you'll see that the 8th element has got those elements have got the similarity. So there is some repetition after the 8 elements. There is that repetition that brings the elements with the same chemical properties. You can start from boron. That is an example. If you start from boron, count 8 as you move. 1, 2, 3, 4, 5, 6, 7, 8. Boron and aluminium in the periodic table that we are using today is still there. So boron and aluminium are still in the same group. However, Newland's periodic table also became obsolete. Why? I mean, was not used anymore. Why? When you look at this group or this arrangement down here, you will see that some of the elements, metals, like cobalt and nickel, were put together with fluorine, chlorine, and bromine, those elements don't have the same properties, but they were grouped together. So, but that is according to him. Look at this. Manganese, when you look at the manganese, phosphorus, manganese, these are elements in group. The antimony, then you have the arsenic, and then we have antimony, then the molybdenum. These elements are also put together. And he could not even give reasons why those elements. That is according to him. So when you do this, this is similar to a calendar. If you have a calendar at home, just look at the calendar besides you. You start from any day, and you count 8 days. The 8th element will be arranged together with the one that you have started with. You just try that one and see whether it works out. And he called this the law of octaves. Those who are doing music and dealing with the notes, probably this makes sense. The 8th and the first one have some similarity in music. That's why they brought in the word octaves, because this word exists in music. So it is a common word in music. So if you are doing music as well, you know what it means here. So these are some of the limitations. Some of the elements were put in the same slot, like this one, 2 here, and this. Halogen is grouped with some metals. I've mentioned that one before. This only worked up to the calcium. When you do that one, do it repeatedly, you will find that after calcium, it doesn't work anymore. Because when you count from calcium, let's start from magnesium here and we see 1, 2, 3, 4, 5, 6, 7, 8. Calcium is there, no problem, because these are the same in the same group. When you move from calcium, let's start from here. 1, 2, 3, 4, 5, 6, 7, 8. The one which is here, the zinc and calcium, the similarity in our modern periodic table, that is not the arrangement. That's how the arrangement is. So because of those problems, this became also obsolete. You should remember the law of octaves, that is the relationship with the first and the 8th note of in the music instruments. So every 8th element has similar properties when the elements are arranged in increasing order of the atomic masses. This is what I was explaining. That if you start from beryllium, or you start from boron, or you start from carbon, and you count 8 elements, you will find that if you start from carbon, you'll find that the 8th element will be silicon. And silicon has some chemical and some physical properties that are similar to that of carbon. That is why in our modern periodic table, they are grouped together. So from there, Newland's periodic table also became somehow obsolete, no longer in use. So another scientist around 1870, Ruther Meyer, this worked with also Mendeleev. They were working together. So I have 2 periodic tables here. So Ruther Meyer did experiments on the atomic masses. So he got elements, determined the atomic masses and the densities, and then came up with a very interesting interpretation from the atomic masses and the densities. He plotted the atomic volume and the atomic masses. This is a very interesting arrangement that came up with when he interpreted his results. Something very interesting. You will see, just have a look at this. you'll see that lithium, sodium, potassium, rubidium, and cesium, they are occupying the same, they are occupying the peaks. And what does that mean? It means that there must be something similar to these elements. And if you can remember the periodic table that we have today, these elements are in the same group. So meaning that he had a lot of the basis in his arrangement, which is still even also which is also still exists even present. Look at the beryllium, the positions they occupy. When you look at the beryllium, look at magnesium. This is a sketch, please. It is just a sketch or the sketch graph of what Ruther Meyer predicted. So beryllium, magnesium, calcium, strontium, and barium. When you look at the positions they occupy, you can easily tell that these elements must be having some similarities. And these elements belong to the same group. The same applies to this is chlorine, this is bromine, and iodine. So those are other elements. When he plotted, actually all the elements were there. We just used this, only these as examples. So he had some basis in arranging these elements according to their physical properties, and that is the atomic mass. His idea was discarded. Even the Chemical Society never looked at his idea, but it was recorded. Now there came Mendeleev, Dmitry Mendeleev. This one is regarded as the father of the periodic table because he's the person that gave almost all the information that was required. So he borrowed the idea of all other scientists that came before him. Dmitry Mendeleev was a Russian chemist, and he was a professor in the University of St. Petersburg. So he was just trying to do the experiments and arrangement of these elements, trying to discover the properties of matter. And then he came with a very interesting arrangement of these elements in increasing order of the atomic masses. So look at, this is the Mendeleev's periodic table. When you look at the Mendeleev's periodic table, he introduces the first person to introduce the idea of the groups and periods. So horizontally, these were the groups. No, these were the periods when you move horizontally like this. And he had groups. So when you look at the Mendeleev's periodic table, he also predicted that in group A, in group 1, for example, there must be, he divided this because he found out something that was very interesting, that copper and potassium had some similarities. But then, they were not the same. Their physical properties and some of the chemical properties, there was some similarity in them. So he created, he divided that group 1 into A and B. And then he put there copper. So you'll see this one happening. Zinc had some similarity with calcium, so he put it there. But the most interesting thing that he did is not about this, the arrangement of this. He left some gaps. That is why he's regarded as the father and the genius person that came up with this arrangement. Can you imagine? He left the gaps for the elements that were not known by that time. I don't know how he came up with that one. But in his arrangement, he thought that there must be an element. You see where I'm putting some of these question marks. That is where he left some gaps. That there should be an element, that means by that time that element was not known. So there must be an element that will have to occupy this position, element this that comes after aluminium. And he called it eka aluminium. Eka aluminium. Eka aluminium. And another element, if you look at this, there is another gap here, so he called that one eka silicon. This is the most important thing that makes him the genius. He predicted that if these elements are discovered, because as I said earlier, these elements were not yet known. If these elements are discovered, then they will occupy these positions. Even most importantly, after leaving the gaps where these elements would occupy, he gave them some names anyway. Eka means after, something that comes after. So he said it is eka aluminium, so that element would come after aluminium. That element, another one would also eka silicon, so it would come after silicon. And interestingly, when these elements were discovered, this one became gallium, and this one was germanium. In his prediction, he even stated the physical properties of these elements. And after the discovery, after 6 or 10 years later, these elements were discovered and they were found to be true. So now the Mendeleev's periodic table has some defects. One of them, when you look at there, because it was according to the increasing atomic number, increasing atomic mass, sorry. So he arranged tellurium is coming before iodine, but he was able to put iodine in its correct position, but that one also is one of the defects. He used our atomic mass, but now this arrangement now is not correct according to the atomic mass because it should be increasing. Look at the cobalt. Cobalt comes before nickel in terms of the masses. So that these were some of the defects of Mendeleev's periodic table, and he formulated the law that states that physical and chemical properties is a periodic function of increasing atomic mass. They are periodic functions of increasing atomic mass. So with that, I would like to give some small exercise. So you'll describe, this would be the simple homework. Oh, let me use a white one. I think that is very clear. Describe Mendeleev's periodic table. That is question 1. 2. A, B. You state the limitations of Mendeleev's periodic table. And 2, you state the law of triads, that is A, and B, you state the law of octaves. Next time, we'll be discussing on the modern periodic table. I hope you have been following. I thank you so much for being with me in this lesson. We'll meet again in the next lesson. Bye.